Thank you all. Next, I welcome Mr. Anson Sando, Head of Energy Programs, IIT Madras Research Park, to deliver the keynote address.
Today, India is already the third largest emitter of greenhouse gas emissions. But at the same time, when you look at the per capita emissions, you'll see that India is 103rd in the same country ranking list. And therein lies the dichotomy of the largest, most populated country in the world and one of the fastest growing economies in current economic terms. And this is at a time when 76% of all the electricity that all of us here consume comes from fossil-based sources. And so I think it is in some sense a fiduciary responsibility that we think about where that electricity comes from. Because I think if you spend a couple of minutes thinking about where you spend most of your time, you'll realize that a lot of us spend that in offices and our places of work. This entire approach initiative that we've set out here is to try and showcase how we can move these places of work, these buildings that we spend so much time in, to become 100% renewably powered. Now, some of the facts that overlay these underlying statements that I mentioned is that India, at the same time, is also estimated to have the largest increase in energy demand among any other country for every single year until 2040. That's the amount of energy and electricity addition that India as a country is going to add to the global footprint. And so it is imperative that India must get to net zero whilst we grow our GDP. Now, if you look at traditionally in developed nations or in the West, GDP emissions has sort of followed GDP growth has followed GHG emissions. Our sense is that we need to decouple the two, that we need to continue growing as a country. There has to be no sort of question around that. But can we grow sustainably? Can we decouple GDP growth and GHG emissions? And we believe that R&D and innovation can get us there by not 2070, but by 2047. Because I don't think there's a better way for us to celebrate a century of our independence. And I'll talk about how we've been doing that at the IIT Madras Research Park. One of the strategies or our overwhelming learning from all of the work that we've done is that any solution will scale if it is cost competitive. Or in other words, if there is a return on the investment that you put in for that piece of technology. And what I'm going to be talking about today is trying to highlight that it is no more just a green building or sustainability aspect, that it is also today the cheapest form of electricity one can procure from any source. That's why this is important, that we can make the argument for the environment, but also add in the economic standpoint, because that's when technology will scale. When I sort of looked at some of the numbers, one statistic sort of stood out, that if you look at the total electricity consumption in the country today, that comes from three sectors. That is the commercial sector, the industrial one, and the residential. They together consume 75% or 3/4 of all electricity consumption in the country today. And so for us, it obviously makes sense to go after this pie because it's such a big component of our energy consumption today. The other interesting part that we learned was that in these three sectors, the commercial category in particular costs the highest in terms of per unit electricity costs. And in fact, when we looked at the numbers, we also found that the commercial tariff across the country, we scanned every state and compared the average rate of power in your homes versus industries versus commercial. And we found that it is on average 40% higher for the commercial category. And so what does that mean? That means that we can obviously go after this sector first because they're paying the highest already for the electricity. So it makes a much bigger argument to start with them. And this is at a time when the commercial sector is estimated to add about 700 to 900 million square meters of urban space every year for the next decade. I want that to be sort of sunk in terms of what that means. Can I provide a different picture or perspective? That means that India, on average, is estimated to add a Chicago-like city in terms of the amount of building and construction every single year for the next decade. That is the amount of construction that is estimated to come into India over the course of the next decade and more. And in terms of numbers, that means that commercial complexes is estimated to triple in number by 2030 compared to 2010 levels. And like I said, this makes sense for the commercial category to start with because they have the highest propensity to deploy capital if there is a return on investment. And that is the message that we want to drive home today because that's what moves the needle. And that's what we want to highlight over the course of this entire sort of presentation and the report that we're going to launch. And if we can do this successfully in the commercial sector, we truly believe that the industrial and high-income group housing sector can similarly follow suit. Now, in terms of our journey, and this is sort of where we sort of wanted to share some of our learnings, our experience in terms of what we've done in this campus. Just to provide some perspective, IIT Madras Research Park is a 1.2 million square feet commercial complex-like setup. For those of you who have not toured it, we are organizing a tour tomorrow. Please do sign up and take a tour of the campus. It is spread across 11.7 acres, but some numbers in terms of electricity consumption. Today, on average, we consume 70,000 units of electricity every day. And that's growing as we speak. And just some numbers for, again, perspective. Our average contracted demand is about 5,000 kVA. I'll tell you why that makes a lot of difference in my coming slides. The total cost of electricity as of date is about 12 rupees 31 paise. We have about 6 chillers that totals up to about 2,900 tons of refrigeration and about 6 diesel generators, about 1150 kVA. All of this will be sort of spoken about a little bit more detail in my coming slides, but just wanted to put that out there for perspective. Now, the first step that we did was just to simply understand what's happening in this building. And so what we did was just look at every single data point that's out there. Today, we're collecting close to 1,200 data points in terms of what's happening in the building. That includes everything from who's consuming, how much they're consuming, and when they're consuming. So we have data in terms of every hour, every minute, and who is consuming for what purpose. I'll tell you why that's important. It'll naturally come out in my coming slides, but it is the only way we'll need to, or we will be able to sort of introduce solutions that are very specific to buildings, because how we operate in the research park as a commercial complex may be different from one that's situated in Bombay or one that's situated in Delhi. So understanding what's happening in the building will be extremely important. And then we want to take that a step further, and that's sort of our plan and vision going forward, is look at everything from the brick to the paint to the wall partitions to see if there are solutions that we can build out there to help enhance or reduce our energy consumption. And the model that we're following is just test, rinse, and repeat, because there's so much we've learned from just looking at some of the data that we've been collecting for the last couple of years. Now, the first thing that I wanted to sort of introduce in terms of the first step that we believe that we should do is that we should reduce before going towards renewable energy use. And the best way to decarbonize actually is just to simply reduce the use of energy. That's something that's very often not given enough of importance. And I'll sort of mention why and how that's proven to become very useful for us at the Research Park. When we looked at the building, we looked at where can we reduce energy usage and how it will move the needle. And one of the points that struck us was that today, in this entire campus, 45% of the energy that we consume just goes in keeping us all cool. That is the amount of air conditioning and cooling that's required for a building such as this. That's why cooling becomes such an important needle mover when we talk about reducing the amount of energy usage in these buildings. I'll give you one example of an exercise that we did with one of our partners, Saint-Gobain. This is something that we did in collaboration with their Saint-Gobain research team here. What we did was simply do a solar heat gain analysis in terms of trying to understand how much natural heat, because of the sun, comes into each block of our building. And guess what we found? And these are all aspects that are highlighted in the report, which we'll share. But we found that the west-facing facade, because we studied the pattern of the sun movement across every day in the year, and found that the amount of heat that is coming into one part of the building, that's the west-facing facade, and think about it, the sun rises in the east, sets in the west. That means that 40% more heat is coming in simply because there's one block that's facing the west. And so what we realized was that if we can introduce solutions to one, simply reduce the amount of heat that's coming in because of natural sources, we'll be able to save about 25% of cooling required in that west-facing facade. That is one solution that can be implemented as we speak in perhaps every building in the country that we are talking about today. And this is just one example. We can introduce this in multiple ways, but the point I want to drive here is that we need to do a comprehensive review of buildings to, one, identify the problems, because honestly, what we've learned is that we can convert that into an opportunity. That's what I wanted to share with this example of what we've done with the Saint-Gobain Research Center. We do believe that going forward, we'll need to do sustainable design, material, and infrastructure. And that should be the norm, because that's really what will help us drive reduction in terms of energy usage before we move towards talking about renewable energy usage. The second part, which is obvious, and I know a lot of people are perhaps a lot more familiar with this, but just stating some facts. Today, solar and wind-based electricity in India costs 2 rupees to 2.50 rupees. What does that mean? That means that today, as we speak in India, solar is the cheapest form of electricity generation anywhere in the world when compared to any source of electricity. It competes with coal, which is today India's dominant source of electricity. We get about 70% of our power from coal-based plants, and they cost on average 2.50 rupees. And in fact, the newer plants, which are mandated to install the emission control equipment, actually cost all the way up to 4 rupees per kilowatt hour if you look at the numbers. And just for perspective, we provided the oil and gas-based plant numbers, which is at the very high 24 to 28 rupees. So what really stops us from converting fully to renewables? It's a very obvious question, right? It's cost the cheapest, so then why aren't we going towards that direction fast? Why aren't we already doing it? Well, we are for one, but there was an obvious question that occurred to our minds, and a lot of people asked us this, was, does India have enough of capacity to meet all of its energy requirements through, say, renewables? One additional exercise that we did was that a single state of Haryana, which is marked in red here, is what we'll need to cover with solar panels, just as an example, to meet all of India's energy requirements today and tomorrow. The overwhelming answer, again, is simply that we have enough capacity in terms of potential so solar and wind and other renewable sources to meet our energy requirements. But then what is missing? The one aspect that we often forget, and I think that needs to be driven home a lot more, is that we need flexibility in the form of storage to match essentially demand for electricity with supply of electricity. That means that solar and wind is available when it is available, so it'll generate electricity as the sun and wind shines and blows, but then we consume whenever we want to consume. The only way to match the two is if we have flexibility in terms of energy storage, and that is really the missing link towards moving towards 100% and 24/7 renewable power. I wanted to point out a couple of specific aspects of what renewables will have to do and understand for the commercial sector. And one constraint, and the more I thought about this, there were two constraints that occurred. One is just the limited amount of space that we have in these buildings and the large investment that's required. But we realized that there's a very interesting way in India to address both of these problems. Open access mechanism allows a consumer like the IIT Madras Research Park to set up solar and wind-based plants outside the campus and generate our power and move that or transport it to the campus for our energy requirements. So there is a way in which we can meet all of our requirements by not only putting it up on our rooftops, but also going outside and setting up our own plants. We've given some numbers in terms of how much that costs. Again, the report will detail some of the numbers. Happy to answer questions around that in the future. But again, there's one aspect that comes out in that regulations are changing, and they're changing because of the fundamental nature of renewable energy. Like I said in my previous slide, they are intermittent in nature. That means that the energy that I generate from my solar or wind plant on, say, August 1st at 12 p.m., initially, because of the grid rules, had 12 months banking. That means I could use it within the next 12 months. If I generated on August 1st, 2023, I could use it until August 1st, 2024, that same amount of power. It then moved to 1 month banking, wherein I had to use it by the end of August. And now it is moving towards a minute or a very small interval through which we'll need to consume that energy. And so the only way to address this is if we have storage that essentially balances demand with supply and provides that rigidity and flexibility for us to move towards 24/7 systems. When I talk about systems, I'll talk storage systems. There are three particular ones that I want to highlight that we have installed and implemented here at the Research Park. The first one being a thermal storage system. Why? Because like I mentioned earlier, 45% of the energy that we consume in this building just goes in cooling. And so what we did was we developed and commissioned, and it's actually implemented at the basement of this block. If anyone's interested, we'd be happy to show you a tour of it. We have built a 300,000 liter thermal storage tank that chills water. Suppose you have excess solar, we chill the water, store it in this tank, and whenever there's a deficit of renewables, we take that chill water and circulate it around all of our offices for our air conditioning requirements. And this works out to be one of the cheapest forms of storage for meeting our thermal requirements. And the use case for this is multifold, and I'll detail what are the use cases in my coming slides, but it serves three purposes. One is for excess renewables to match demand and supply. The second one being peak tariff. That means when the clock strikes 6, my electricity cost from the grid actually costs me 25% more. So guess what we've done? We've essentially turned on the thermal storage systems at 6 p.m. every day so that I can get cheaper power, just straight up. The third use is that we found sweet spots, and this is again something that we've done with our data, in that when you can operate the chillers at a much higher loading percentage, it happens to be at a much better efficiency. So using the thermal storage systems helps us, essentially operate our chillers much more efficiently. The second storage that we've built and deployed, and this is actually just got deployed yesterday. There's a this is a lithium-ion battery storage, which is set up as a container. Again, the two things that this is doing is whenever there's excess solar and wind, we store it in these batteries, and we use it during two times. One is during the peak tariff hours. So like I said, when the clock strikes 6, I can use it from my battery storage instead of paying 25% more for my electricity at the same time from the grid. One problem that everyone sort of pitched and sort of put forth against us is what's going to happen at the end of the life of the battery. And what we're doing is also recycling some of the batteries to essentially look at recovering the materials. And as per our current data, we were able to recover almost 90% of the material at a 98% purity. That means that these batteries that are at its end of its life can be recycled and reused for its next life. Essentially, we want to sort of close the loop and look at a circular economy. The third battery, which is an interesting exercise that we've done, is an LTO battery. And why is this? Is because of a fixed charge. Now, if you look at your electricity bills, not so much apparent in your home electricity bills, but if you look at your office electricity bills, there's two components. One is a fixed charge. That means irrespective of how much you consume, there is a fixed charge levied to you as a building to just draw power. Essentially a ceiling of how much you can draw at any instant. That ceiling for us is about 5,000 kVA, which I earlier mentioned. And the per kVA charge for that is about 562 rupees. That totals up to about 28 lakh rupees of fixed charges that irrespective of whether I consume 1 unit of power or 1,000,000 units of power, I will still have to pay. Is that charge too high? Do we really need it? We looked at, again, the data, and we found that when we analyzed all of the data at the research park for an entire year, we found that only 40% of that 5,000 I'm using on average per minute. And so if I can just shave off that mountain that you see on top there, it's going to help. How can we do that? We essentially utilize what we're calling the LTO, or the lithium titanate batteries, which essentially has fast charge and fast discharge. And if you can see the yellow bar here, bring it down to that level, and if we can essentially use this battery for about 15 to 20 minutes in a day alone, I can, on average, rough calculations we've done, save about 5 to 10 lakh rupees because I can shave off that much of my fixed charges. That improves with the more amount of storage that I have. So from the yellow line, we'll hopefully get to the green line sometime. But we believe that if we can do that and just essentially plan our operations, optimize it in such a manner, then we can actually save about 5 to 10 lakhs straight off the bat. So what we're using for that is smaller but faster batteries that can essentially fast charge. That means in our terms that we use is 5C to 10C fast charge and discharge. And these are designed for this precise need of shaving off mountains like the one that you see here. And that's actual data that we've captured from our operations here at the research park. Finally, the piece that brings this all together is we have such a variety of energy generation sources, including solar, wind, hopefully nuclear one time, 3 types of storage, which I just mentioned, and a multitude of consuming needs. There are chargers, electric vehicles that are going to come out, the air conditioning that's required, and different loads. All of this needs to come together in a centralized system that can manage and operate this real time. And this needs to be done 24/7. And if we want to do it through RE, then we need a comprehensive and robust system that can manage this real time. And what we've done for this is an energy management system that can essentially control. So when it strikes 6, my energy management system is going to automatically trigger my batteries and my thermal storage to run these storage systems such that they save me power and electricity automatically. And of course, We're also trying to design this in an app so that we can also use it based on user control. So I can tomorrow take out my phone and actually discharge my batteries if I'm actually looking at doing that. And what it is hoping to do in the future is continuous learning in terms of reducing the faults, higher efficiency, and essentially increasing our savings. Now, having said all this, the obvious question I think many of you must be thinking by now is what's stopping us? One of the factors that I mentioned as I started was that if you want to go green or renewable, the economic case also needs to be there. Otherwise, this can go up in a presentation, we can talk about it in several conferences, but what's really going to make a difference is if we can demonstrate the economic case for this, and that's what we've set out to do at the Research Park. And I'll share with you the numbers for this, but before that, we wanted to highlight why this economic case is sensitive and what it is sensitive around. 3 factors. One is the capital costs, second is the usage cycles, and third is the amount of renewables going into my storage systems and the amount that I can directly use. I'm not getting into the details in the interest of time, but happy to sort of share the report to anyone who's interested, but I'll talk straight to the numbers. What's really the green print? We've done all of this. Today at the Research Park, I mentioned earlier, we pay on average 12 rupee 31 paise per unit of electricity. I'm proposing, and we're halfway there to implement that. If we go 90% renewables with all my storage, including capital costs, depreciation, and every cost head factored in, the per unit cost actually comes down to 9 rupees 80 paise. And what that means also is that I save on average 33 lakh rupees for the Research Park every month. That's today's costs. And as we go forward, one thing is going to sort of be certain. Electricity prices, as we've seen in Tamil Nadu, is going to go up. The cost of renewables and storage is going to go down. And so that 33 lakhs that I'm looking at today for the Research Park, per month, mind you, is going to only increase over time. And that's the message that we want to drive home, that it is now possible for a commercial building to go out there, do this, and also save costs. So we're not just doing this for the planet, but just look at your pockets. There's a 33 lakh bounty, open, ready for you to take up. Summarizing what I mentioned, the cost goes down to by about 24%. That's based on today's numbers. The average ROI, as per today's numbers, again, is about 5.5 years. What I want to highlight is essentially the fact that this is something that is an approach that is scalable across the country. There is about 50,000 odd commercial complexes today as we speak that can take up this approach, decarbonize, and save costs. Tomorrow, there's about 1 billion square feet that is yet to be built. If we build right, follow this approach, same message that we want to drive, that it is going to be environmentally friendly and also save you costs. And as the costs decline, the same approach can be moved towards the industrial sector and the high-income group housing sector, which, guess what, is today consuming 75% of the country's electricity. And so if we can make a difference, then this is where we can start. And so I go back to asking the question, can all commercial, industrial, and high-income group housing go green now? Given this is essentially the summary of what we've put out as a report, which we'll be launching just right after this. And if I may, and I pardon, but I like to close with a wartime analogy. If you think about it, when we look at climate change and its effects, we're actually at war. And we're building an army out here. This is in some sense our fortress. And on behalf of the IIT Madras Research Park ecosystem, I'd like to invite each and every single one of you that's working on climate tech solutions to join us, because we'll need every single one of you to join, because that's the only way we'll be able to scale and scale in time for us to really solve this problem at scale. And with that, I will close, and in the interest of time, take a couple of questions if we do have. But thank you.